This video is going to introduce the terminology parameters and statistics and help us to learn how to identify the parameter of interest and find an appropriate statistic to use as an estimate for that parameter. This material is covered in section 3.1 at the very beginning. It's an important foundation for the work we're going to do throughout the rest of the course. We talked back in chapter 1 about the idea of statistical inference. Remember that statistical inference is what happens when we're interested in a population that it's too large or difficult to collect data from every member of the population. And so in this case, we'd select some members of the population to form a sample and then use the information in the sample to try to make guesses or estimates about what's true in the population. And this process was called statistical inference. And we talked about how important it is to have a sample that's representative of the population, preferably by taking a randomly selected sample from the population. And we're going to throw in some new vocabulary here. When we talk about the numbers that we use to summarize the data in a population and the numbers that we use to talk about data in the sample. When we talk about numerical summary measures, we differentiate between numbers that are summarizing data in the entire population and numbers that are summarizing data from just a sample. A parameter is the name that we give to a summary measure that's summarizing data for the entire population. One thing to notice is that the word parameter and the word population both start with P, and parameters summarize the data in the population. So the P's go together. A statistic is what we call a number that summarizes the data collected from a sample of the population. And again, statistic begins with S and sample begins with S. And statistics are numbers that are calculated to summarize the data in the sample. So remember, the P's go together and the S's go together. Some examples of parameters in statistics. We'll start with the parameters. The mean score among all students who took the SAT in 2020 is 1,051. Here, because the data were recorded for all of the students who took the SAT, this mean is a mean for that whole population, and we'd give it notation mu, population mean, is 1,051. Another example, out of all Vermonters who voted in the 2020 presidential election, 66.1% voted for Joe Biden. Again, this number came from looking at all of the Vermonters, that is, who voted in the 2020 presidential election. And so this percentage is actually a population parameter. And if I wanted to write that with correct notation, I could write it as the population proportion, P, is equal to 0.661. That's my 66.1% expressed as a proportion. Now let's look at some examples of statistics. An example of a statistic: among a random sample of 624 Vermonters who have credit cards, the mean credit card debt is $4,653. In this situation, this mean was calculated only using data from a sample, and because of that, it's a statistic. We use the notation X bar to tell us that this is a sample statistic, and that sample mean is 4,653. Another example, Pew Research surveyed 3,930 randomly selected U.S. adults and found that 29% believe that the amount of gun violence in video games contributes a great deal to gun violence. In this case, the data came from a sample of the US adults, and so this proportion that we're interested in here is calculated from a sample. P hat, the sample proportion, is our statistic, and expressing that percentage as a decimal, P hat is equal to 0.29. So just coming back to talk a little bit more about parameters. The value of a parameter can be calculated only by collecting data about every member of the population. If we can collect that information, the parameter measures what the true value is in the entire population. For instance, what is the true mean among everyone in the population? Unfortunately, usually the population is too large to collect data from the whole population. And so most of the time, the true value of the parameter is unknown. Statistics, remember, are calculated from the sample data. When we don't know the true value of the population parameter, we can calculate a sample statistic to estimate it. The sample statistic in this situation would be called our best estimate. Let's apply this vocabulary to an example. So earlier I talked about a sample that looked at credit card debt in Vermont. Among a random sample of 624 Vermonters who have credit cards, the mean credit card debt is $4,653. So thinking about our vocabulary here, right? Our population, the group that we'd really like to know about, well, randomly sampled from Vermonters who have credit cards, so presumably would be interested in all Vermonters who have credit cards. And since we're talking about the mean credit card debt, the parameter that we'd like to know would be the population, mu. The mean credit card debt among all Vermonters. That's what we really want to know about. But because it's too much work to take data from every single Vermonter with a credit card, they took a random sample of 624 Vermonters who had credit cards. That's our sample. From that sample, they calculated the sample mean, X bar, which was $4,653 of credit card debt. That is our sample statistic. And that sample statistic is also going to act as our best estimate for the parameter. So again, just getting used to this vocabulary and thinking about applying it to this example. Now, in Unit 2 of the textbook, We're going to start in chapter 3. In this chapter, we'll be estimating population parameters based on sample data using something called confidence intervals that'll give us an idea of how large the margin of error is around our estimates. In chapter 4, we're going to be testing claims about population parameters using something called hypothesis tests. This is where we'll learn about what it means for things to be statistically significant and how to decide if a result is statistically significant. Notice in both of these, I am making inferences about population parameters, and in both cases, I'm going to be using sample data to do so. So in both chapters, it's going to be really important to be able to identify the parameter of interest and which statistic we should be using as the best estimate for it. So how do we determine the parameter of interest and which statistic will give the best estimate? Well, the way that we figure that out is by figuring out what kind of variables we're working with. That will guide the kind of parameter we're making inferences about and which statistics we should be using from the sample as our best estimate. And I have this table to break down what we would be using in each situation. When we have one categorical variable, we're estimating the population proportion P using the sample proportion P hat. When we have one quantitative variable, we are estimating the population mean, mu, using the sample mean, x bar. My bar didn't print very well. When we have two quantitative variables, we're interested in understanding the correlation in the population, rho, and we estimate it with the sample correlation, r. With two categorical variables, we're interested in the difference in the population proportions, P1 minus P2, which we estimate using the difference in the sample proportions, P1 hat minus P2 hat. And when we've got one categorical variable and one quantitative variable, the parameter that we're going to be interested in is the difference in the two population means, mu1 minus mu2, which we'll estimate with the difference of sample means, x bar sub 1 minus x bar sub 2. I strongly recommend making a little copy of this table and putting it someplace handy so you can refer back to it for a while you get used to using it to guide you into making these choices. So a quick example, is fatherhood related to longevity? Among men in the United States, we want to know, does lifespan differ between men who have children and men who don't have children? For a random sample of 2,000 men who died during the year 2012, researchers recorded their lifespan, their age at death, and whether they had any children. The average lifespan among those who had children was 78.4 years, and the average lifespan among those who had not was 64.9 years. Okay, so the population that we're interested in is going to be men in the United States. So our population, all men in the US. The parameter that we're interested in with correct notation, well, let's see, what kind of variables do we have? We have their lifespan and whether they had any children. Lifespan is quantitative. Whether they had children is categorical. When I've got one quantitative and one categorical variable, I'm going to be interested in a difference in means. The difference in the population means, mu1 minus mu2, would be my parameter. That would be the difference in the mean lifespan between men who have children and men who don't. Say between men with and without children. In the population of all men in the U.S. That is the parameter that we're interested in. Since we don't have that data from all of the men in the United States, we're going to have to use our sample data to estimate it. The sample is the 2,000 men. And the best estimate for the parameter is going to be the difference in the two sample means. The mean from the men with children was 78.4. The mean among those without children was 64.9. And so as we look at the difference here, we get a difference in mean of 13.7 years. And that is our best estimate. We'll do one more example. What percentage of U.S. adults support raising the minimum wage to $15 per hour? Monmouth University pulled a national random sample of 802 adults aged 18 and older. Among people in the sample, 425 of them said that they support raising the minimum wage to $15 an hour. Okay, so again, we'll think about our population. It was a national random sample of adults age 18 and older. So be all adults 18 and older. In the US would be the population that we're trying to learn about. What we want to know about them, our parameter. Well, let's see. What kind of variable do we have? For each of the people in the sample, they were asked whether they support raising the minimum wage to $15 an hour. So we've got one categorical variable. Whether they support raising minimum wage. With one categorical variable, the parameter I'm interested in is going to be P, the population proportion, and that would be the proportion who want to raise the minimum wage to $15 an hour. In the population of all U.S. adults. That's what we're trying to estimate. Now, since we can't collect data from every single U.S. adult, they used a sample. The sample was the 802 adults that they randomly chose. And then the best estimate for the parameter with correct notation When I'm estimating the population proportion, the best way to estimate it from the sample is with the sample proportion, p hat. In this case, there were 802 adults in the sample. 425 of them wanted minimum wage to be raised to $15 an hour. That comes out to 0.53 or 53%. So again, the way to decide what kind of parameter we're interested in and what statistic to use as the best estimate is to figure out first what kind of variables I have and then use that to guide my choice. So in the handout that you have to finish up for today's class, there are a series of little scenarios for you to identify the population, the parameter of interest with the correct notation, the sample, and the best estimate for the parameter. Once you're done, you can submit that using the link in the Course Materials tab. And once your work is submitted, you will be given access to the solutions so you can check your work. And if anybody has any questions, we'll go over those questions in class on Thursday. Last thing I'll mention for today as a lead into Thursday's class is the idea of sampling variability. If we were to take different random samples of the same size from the population and use them to calculate the best estimate for a population parameter, the estimates will vary from sample to sample. So for instance, if we took a different sample of 802 randomly selected US adults, it probably wouldn't be exactly 53% of them who believed that minimum wage should be raised to $15 an hour. Probably get some other value for our sample statistic. And if I took another random sample, I'd probably get another different result again. It's likely that they'll be close to the same, but they won't be exactly the same. So in the second part of section 3.1 on Thursday, we will be learning about how these estimates vary around the true population parameter. Again, please make sure you complete the handout and turn it in by Wednesday night using the link in the Course Materials tab. Have a good day, and I will see you on Thursday.